So, welcome to the Oskar Klein Memorial Lecture of 2011. And it's a pleasure for us to have Professor Joseph Silk here today. It's a Klein lecturer. But before I introduce him, I just wanted to say a few words about the Oskar Klein medal. So, and Oskar Klein. So, Oskar Klein was born in 1894, and he was a professor in theoretical physics here in Stockholm. At that time it was called Stockholm Högskola, and later it became Stockholm University. Oskar Klein is known for many things in theoretical physics. For example, the Klein-Gordon equation, Klein-Shina formula for light scattering, and the Kaluza-Klein theories with extra dimensions. It seemed really far-fetched at that time, but today it's become much more popular, very much due to the interesting string theory, which seems to indicate that we have extra dimensions. And these memorial lectures we have had since 1988, and we're very happy to have support from the Royal Academy of Sciences through its Nobel Institute for Physics that supports these lectures. And this year, as I said, we'll have Professor Joseph Silk as the Klein lecturer. So Joseph Silk is currently a professor at Johns Hopkins University in Baltimore, and is also affiliated to Institut d'Astrophysique de Paris. Maybe I got the pronunciation partly right, I don't know, in Paris. And he's worked on a lot of things. He's worked on cosmology, astrophysics, and he's probably most well known to most physicists for something called Silk damping, which has to do with the damping of the plasma in the early universe when the cosmic microwave background radiation was emitted. And Professor Silk had his undergraduate education in Cambridge, and later he moved to the US and got his PhD from Harvard. And after that he's been all around the world, in many different places. And he was a professor at UC Berkeley in California for many years, until in 1999 went back to England as a professor at the University of Oxford, professor in astronomy. And since then, as I said, he's also in Paris and in Baltimore. And even if Joe is very well known for his contributions to the cosmic microwave background radiation, I have known Joe since a long time, and Joe's knowledge about astrophysics and cosmology is very broad. So if you have some questions you've always wondered about, I'm sure you can ask Joe later, and if he doesn't have an answer, I'm sure he will know what kind of experiment or observation you should do to find the answer. Okay, and as I said, this Klein lecture series has been going on since 1988, and I just wanted to show the previous speakers that have received the Oskar Klein medal. And we've had a long tradition of having many famous theoretical physicists that have received this prize. And with these words, I hand over to Joe, that will present this year's lecture. Yeah.
Okay, so it's really, did everyone hear me clearly?
No. You need to fix the microphone.
Okay, that's better. Well, it's really a great honor to be part of this wonderful tradition. I'm even going to touch in my lecture on one of the consequences of Oskar Klein's contributions to cosmology towards the end. And so let me begin. I gave a very ambitious title here. I'm going to tell you some stories, partly about the Big Bang and what we're doing to resolve outstanding questions and where we're going. But let me begin with the person who really we have to blame for much in modern cosmology. Of course, Einstein set up the theory of general relative gravitation. And as you all know, I'm sure he basically introduced this radical idea from of the fact that the curvature of space was a new way to understand the effects of the gravitational field. And of course, I've expressed his theory in words here, but if you want to be a little more mathematical, one can write it in tensor form, but it doesn't really matter. On one side we have gravity and expressed by the curvature of space. So near a black hole, for example, space is highly contorted. Near the sun, it's very slightly contorted. So you can even, test the effects of Einstein's gravity near the sun, for example. It was tested within a few years after he published the first paper, and of course Einstein became a world hero almost immediately in 1919 when his theory was vindicated. Now, as far as cosmology goes, Einstein suffered to some extent from the general worldview of his time, which was that we live in a static universe. And he missed the fact that in these equations was buried the possibility that the universe could be expanded. And in order to make the universe static, Einstein had to introduce a force to counter gravity to stop the Earth collapsing, which we call now the cosmological constant. And he later admitted, once expansion was acknowledged, it was a great blunder he'd made. But as you'll see towards the end of my talk, his ideas have come back to haunt us. Anyway, the story of the discovered expansion can be attributed to Hubble, who at Mount Wilson in Pasadena was able to measure distances to galaxies in a fairly unique way for the time. And others had previously worked out the fact that the galaxy spectra was slightly shifted to the red, indicating recession. And Hubble made this plot of the velocity of the galaxy versus its distance from us, going over the nearby few million light years from us. And so this is velocity goes as distance, which means that if you extrapolate back, there was an origin, things are moving away, they once came from some hypothetically infinite and compact volume, infinite density compact volume. And this later got dubbed, of course, the Big Bang. Now, let me tell you one of the more amazing stories about this, which was only unveiled in the past month or two. And so, of course, before Hubble announced his results in 1929, I think Alexander Friedman, working in Russia, had realized there was an expanding solution to Einstein's equation. So he, in some sense, is one of the founders of a predictor, if you like, of the expanding universe. He wasn't the only one, however. Independently of Friedman, Georges Lemaitre, who had done his PhD at MIT, got interested in cosmology as one of the implications of general relativity, he not only discovered independently that the universe could be expanding, but he realized from the data available to him in 1927, 2 years before Hubble, that indeed there was evidence for expansion, and you can see his numbers are much like Hubble's numbers. Now, the amazing thing is, this figure never saw the light of day, because it was published in French, actually. And so the question is, what really went on? Did someone, and there have been many conspiracy theories about this, did someone suppress the public? Because his work was translated in 1931, appeared in the Monthly Notice of the Royal Astronomical Society. So what was the figures, was the data suppressed? And it turns out, this came up very recently from a study of the archives, that indeed there was no conspiracy. Letters have been found in which the main point is that when Lemaitre says, you can't read this, he translated the article himself, and he thought it was not appropriate, there was no relevance really in his publishing the data he'd used and his fit to the data, because Hubble in the meantime, 2 years later, had already done the publication. So Lemaitre in total modesty said, it doesn't matter. But in hindsight, we can see that he got there before Hubble, and what we call the Hubble law should really be the Hubble-Lemaitre or Lemaitre-Hubble law. It's a very interesting story, and this only came up, it was only published in Nature just months ago, that discovered this correspondence between Lemaitre and the editor of the Monthly Notices, who translated who published his version in English for the first time in 1931. Anyway, but of course, Lemaitre was put slightly on the sidelines. Nevertheless, we have Hubble and Einstein confirming the theory of the expanding universe in this photograph, classic photograph. And it really became notorious, the whole idea of the expanding universe. It captured the public imagination. This is a cartoon from the 1930s in which Willem de Sitter, who also worked with Einstein, and he and Einstein jointly published what has become one of the standard models of the expanding universe from Einstein's theory, the Einstein-acidic theory, which is pretty close to what we actually model the expanding universe with today, for apart from one detail, which I'll come to later. Anyway, so there we have things as they were in the 1930s. Where have we got to today? Okay, so this is another incredible part of the story. We realize now that the data that Hubble and Lemaitre used are in this tiny, tiny part of this diagram of velocity versus redshift. I've changed the axis slightly. And in fact, were dominated by enormous scatter in the data, okay, for various reasons. And in fact, they had to have a certain amount of intuition, in fact, to fit a line through those data points to get a slope. Anyway, the modern data, you can see, goes on and on and on. And indeed, you can see at the end this very slight deviation. And this is the deviation that led to this year's Nobel Prize, because the faintest galaxies, in fact, deviating from they're a bit fainter, they're accelerating from us. And so that only came out very recently, plastic discovery. Anyway, but apart from that, there's very, very strong evidence for the expanding universe. Okay, so to some extent, the whole field of cosmology was pretty static for the next decade or two. People gathering data, pushing the expansion off further and further, but there were no new insights into the theory of what soon came to be called the Big Bang. And those insights only came about when a whole new sector of physics got interested in the theory of the expanding universe. And these were the nuclear physicists. And so this began around 1949, a year or two before, and this led again to really an immense breakthrough in our understanding of the Big Bang. And really, this was led by George Gamow, a Russian emigre who ended up in the US, and his students and postdocs. And they realized that there was, if they assumed the beginning of the universe, this very dense state, was also a very hot state, one then would imagine as the universe expanded, it went through the same sort of phase that you see now in the middle of the sun, where nuclear reactions convert hydrogen to helium. And he argued maybe all the chemical elements for which you're made of could be made in the first minutes of creation, as he put it. Now, it turns out that he was wrong. We later realized that most of the elements could not be made that way, because there was an unstable element in between that stopped it, but the light elements could be made. Helium in particular, the second most abundant element in the universe, could be synthesized, almost certainly was synthesized in the first minutes of the Big Bang, because stars don't do it. There's not enough stars, they're not old enough to have made all the helium. Anyway, and this led to a prediction that I'll come to it again in a moment, that if the universe, the Big Bang, really was hot, there should be some fossil glow around today. But his prediction was completely forgotten, okay? But that was the consequence of this great insight. So how then do we explain not just the light elements, but the elements that we're made of? That also came from the nuclear physicists, who realized that when you take a star, rather more massive than the sun, it rapidly gets hotter, burns its hydrogen, turns out to helium, and then the helium burns up, makes carbon. As it evolves, finally you get a big core of iron in the middle, and iron is a very stable element. You can't extract any more energy out of it, and the whole thing collapses, because there's no more energy to keep the star extended. And this explosion leads to what we call a supernova, which scatters the debris of this star throughout its vicinity, and it's from those cinders mixed with these little clouds that that explains why planets and other stars are made and why we're here. So this then was the next breakthrough from nuclear physics, and these are the people that made their breakthrough, the Burbages, Fred Hoyle, and Willie Fowler. And as often happens in physics, The recognition for this amazing discovery went to, in fact, just Willie Fowler, but the others all played a very important role. Fowler, of course, did other things too, as well as this. Anyway, so that was the contribution of nuclear physics. Now, to continue the story, let's go back to the astronomers who then took up Gamov's quest for the fossil globe. Gamov had predicted a paper saying the universe should have some heat in today, but people have forgotten it. So quite independently of his prediction, Penzias and Wilson rediscovered this fossil globe using a microwave telescope and finding that there was a background radiation which seemed to be consistent with the hypothesis that came from the Big Bang at a temperature of only 3 degrees of absolute zero, purely emitting in the microwaves, covering the sky. And in fact, in hindsight, this is not such a hard thing to find, because if you put your television set out of tune in between channels, the noise on the screen, 1% of that noise is the cosmic microwave background. So it's a glow from everywhere filling the sky. And this is the fossil radiation from the Big Bang. And of course they too eventually got the Nobel Prize for that discovery. Now let's try to get closer to modern cosmology and where this has taken us. Well, it's one thing finding this fossil globe, but the next thing we have to try to understand is why we're here. The universe is full of structure, full of galaxies. So imagine this is what we call a space-time diagram. We're in the middle, the Big Bang is on the outside. Okay, and so the early universe was dense and hot. It was like you can't see through it, even with a big telescope, they're looking through a fog. The fog ends at roughly this time when the ionized plasma neutralizes, becomes ordinary atomic height. As the temperature drops, it expands. And so when we look with radio telescopes, or with any telescopes, in principle we can look back to when the universe was roughly 1,000th of its present size. However, one of the predictions then, if galaxies are formed by around today, what was realized was this background radiation that was seen, predicted by Gamow, essentially discovered by Wilson, was incredibly smooth. There was no sign of structures in that radiation. Therefore, the inference was structure had grown by the effects of gravity. I'll explain a little more about that later on. We call it gravitational stability, but taking small things to big things. But the consequence is you should expect to see tiny temperature variations if the structure is formed by today. And so the period in between now, lit up by the galaxies around us now, the most distant galaxies, and where we can see the fluctuations, we sometimes call those the dark ages. It's very hard to do much astronomy there. There's nothing really there, very little there apart from a little bit of gas, microwave background radiation. But we look for the first galaxies by trying to explore, where they might have formed. Anyway, imagine two points on this sphere in the universe, imaginary sphere, from which we can see without radio and microwave telescopes. If the points are far enough apart, then it's interesting. Here is the Big Bang. This is the radiation that could have traveled in the age of the universe from a point of the Big Bang. And this is what we call our past light cone. So if points are too far apart, there's no way, unless you can exceed the speed of light, they could be connected. So what this is telling us is that temperature fluctuations really come from, if you measure them, they come from close to the Big Bang. Okay. Thank you. So in some sense, if we see variations in temperature on the sky, it's not exactly 3 degrees, tiny differences, then we're measuring properties of the very beginning, as well as the seeds of the structure. So that's what we've learned. Well, these fluctuations were looked for a long time, and they were finally found. So here they are. I'll explain the problems in front of you in a second. But the COBE satellite, launched in 1990, measured the microwave background, and these are the differences in temperature. This spot's slightly colder than the average by a fraction of a percent. Other spots are slightly warmer. And so these are the mysterious fluctuations. And of course, these equivalent scales are very large indeed. And a more recent satellite, this is 7 years of data from this satellite, has remapped this with very high resolution in angle. And you can see now this is the plane of the Milky Way, which is removed from the picture artificially, but you can see the regions which look colder now break up into tiny structures, and these then are the seeds from which structure began. Okay, so, and this detection with the COBE satellite was again awarded Nobel recognition a few years ago, and so Smoot was the person who was head of the experiment that measured variations in the temperature, but the other great discovery by the same satellite was that the fossil radiation was a perfect black body, which is proof that it really came from a perfect furnace, the Big Bang. And so that's this spectrum here, and this is probably as good a black body as we could ever measure anywhere, but these error bars, which in statistical parlance are 400 sigma, 470 the incredibly precise. This is in the sky, okay, testifying that we really do have a Big Bang. Okay, so this then is what you might think of as all standard stuff. Okay, so there's one new development that entered the theory, this time led by the astronomers. Okay, so around 1950s, it was realized that there was a new thing in the universe that we could not see with our telescopes, and this is dark matter. And one of the people who pioneered this in a time when women were rather rare in astronomy, and so when Vera Rubin had to take data on nearby galaxies on Mount Palomar, she had to go down at night to use the facilities. There was nothing for women at the top, so or after she'd observed for the night, she'd have to go down in the morning, whereas the men, of course, had their accommodation at the top. Things have changed since. But anyway, what she realized and discovered, and was the first to map out, was the fact that as you look at galaxies like this, you trace the stars further and further away. You notice there are fewer and fewer stars. Most of the stars are in this round region here. She found the velocities at which they're orbiting stay roughly the same. And these are what we call rotation curves. And this means that if the mass were concentrated in the center where the light is, the velocity should get weaker as gravity gets weaker. They should fall off slightly. They don't. I mean, this is what we call Kepler's laws. We don't see Kepler's laws today, telling you there's lots of dark matter, maybe 10 times as much dark matter as you see in stars. In galaxies, like our own Milky Way, for example, and in many nearby galaxies. These are a sample of many different galaxies seen on this plot. Okay, so this takes us out to hundreds of thousands of light years around galaxies like our own, full of dark matter. Another discovery that was actually made even earlier in 1933, but also not understood until much later, was that galaxy clusters, and Fritz Zwicky was a Swiss-American astronomer who pioneered cataloguing galaxies, and he realized that in this cluster of galaxies, the galaxies like this would fly apart were it not for the effect of dark matter keeping them basically in one place. And the fact that we see galaxy clusters is basically a testimony to dark matter. And with modern developments, one can actually treat gravity like a lens. This is a lens moving across the image. You can see this lens distorts the images behind it slightly. Okay, so gravity focuses light, acts like a lens, distorts light. And in the actual data, you can see these tiny distortions, and you map them out, and this actually, this is the map of the distortions. You can see this is a dark matter map. You can't see the dark matter, it's indirect. This is dark matter telling you that there's 10 times more dark matter than there is stars in galaxies in this galaxy cluster. So this is now on million parsec scales, million light year scales, okay? Well, we don't stop there. Again, the astronomers go on, and on even larger scales. Now this represents an entire cluster of galaxies, but as seen when you map it out, not in actual space, but using the redshift through Hubble's law as a measure of distance. And you find, because there are random motions in the galaxies which you misinterpret as distances, then the galaxy coming towards you seems to be slightly closer, one moving way slightly further, that gives you this fun distortion. But at the outside of the cluster, things are really falling in, and so you have this pancaking effect, okay? And so these distortions, because you measure redshifts and you measure distances, tell you all about dark matter on this larger scale. And indeed, if you look now at deep galaxy surveys, this is one of them, in redshift space you can see these weird concentrations, and these weird concentrations are the effects of distortions like this due to dark matter on 10 million parsec scales. But it doesn't stop there, just to take one step further, and again, you can do even better, and so I'm going to again tell you about this in a moment, but we believe that the fluctuations that were there that gave rise to galaxies were in the early universe, which was dominated by radiation, were basically like waves, oscillations, like sound waves in a plasma of matter radiation. Anyway, these are oscillations, and you can measure their imprint on the density fluctuations by basically you can measure distances that are along the line of sight, but from the redshift and from the angular extent of the sky too. So you can map out structures in the distribution of ripples in the density field. And this is what you expect. So this curve represents density fluctuations in the universe, okay, going from very large to very small scales. And what you expect if there is, if you change the amount of ordinary matter into dark matter, if you make it more important, is the strength of these ripples gets stronger and stronger. So if you look for ripples in the density fluctuation, we call this the power spectrum, it's another way of measuring dark matter. Now we're on 100 megaparsec scales. So the point of this is to show you that we can measure dark matter from tens of kiloparsecs, galaxy scales, up to hundreds of megaparsecs. So dark matter really is something that we can understand, that we can map out, and we know it's there. I wouldn't say we understand it, that's too soon. Okay, so again, one more, a whole, almost I would call it a paradigm shift in astronomy happened in 1980. So this is the next stage in the story, and this was, again, it's interesting. You see these changes when a whole new field of physics takes an interest in cosmology. This time it was the turn of the particle physics, because they realized that to build a particle accelerator, we have a very good one going on now producing exciting physics in Geneva, could only measure energies up to some, in this case up to a few TeV. But really, the expanding universe predicts energies near the beginning that are millions of times larger. Okay, so it's a natural accelerator. So one can do all sorts of particle physics by, now you can't repeat your experiments, we only have one Big Bang, but at least you can study the debris and treat it like an experiment. Okay, and they realized this was a wonderful way to study physics, and the first thing that was done was to address one or two of the paradoxes of the Big Bang. Okay, and this is the way it was approached. So at low energy in the universe, that we, in this room, etc., the electromagnetic force is very different from the nuclear force, okay? That's on very tiny scales. We don't notice it. Our bodies are controlled by weak forces. But as you go to high energy, we know the force strengths converge together. Okay, and there's an epoch which is calculated, and it's a unique epoch thanks to a theory called supersymmetry, which may well be confirmed or may not be confirmed by the Large Hadron Collider in the next months, we don't know, or years. But it's a prediction anyway. And given that theory, they converge at a unique point, or in general they'll converge somewhere, it may not be a unique point, but this we call grand unification, and this is incredibly high energy, again, billions of times more than you can reach with the LHC, but it does predict there was this unification at high energy. Now, gravity is the one thing missing, okay, that doesn't fit into this particular theory at the moment. That's where string theory may come in. But in general, let's focus on this. So one of the predictions that was realized as the universe cools down from high energy to low energy is that this is a phase transition. And one analogy that's been given is imagine a frozen lake melting, energy is released, okay, under the ice. Fish can stay alive in a lake covered with ice. And that energy release, in this case, could be so dramatic as to cause the universe to expand incredibly, okay, far, okay? And so that looks something like this. These were the pioneers of this idea in 1980, Andrew Lindy and Alan Guth. And what they realized was that this injection of energy, and I have to draw it in this two-dimensional way to give you some feeling, so there's a wrinkled balloon expanding many, many times. You can understand from what you might imagine might be some generic initial conditions, some arbitrary geometry in the early universe, that if you expand enough, it stretches out, and locally, this two-dimensional space becomes flat. Now, we happen to measure with high precision, and I'll show you that again in a moment, the universe is Euclidean. It really is very, very flat in the three-dimensional sense. And you can explain that, but also understand why the universe is so big. You can start a very small universe, and it will expand immensely and become enormous. And so those were two of the predictions of the inflation theory. As I say, it is hard to understand without lots of hand-waving, at least at this level. But let me show you then one or two schematic indicators of what this does for us. So prior to the inflation theory, this is what we thought of as the Big Bang of Einstein, de Sitter, etc. So we can see about this far in the universe. Okay? With our biggest telescopes, we can basically see back some nearly 15 billion light years. Okay, but there's a whole lot of stuff out here that we can't see. Nevertheless, the theory expects a certain size of this universe, depending exactly on your precise measure of parameters, but it's not, it's some finite size. It's generally thought to be possible. Okay. However, what inflation theory, no, that's not necessarily the case. That's close to what we measure actually. The universe is somewhat, constrained to have a geometry that's not very far away from the simple geometry of Einstein and consider, which means a finite universe. One could debate just how big it might be, but what inflation says is something quite different. That it tells us that the universe is enormous. In fact, it could be infinite actually, okay? And that we're just some tiny part of it, and that this is a prediction of explaining that we're in no very special place at all. If I went back to the previous slide, we would be rather special. The universe might ultimately be like this, we're over here. But in fact, the part we can see is just some tiny part in some enormous, possibly infinite universe. So the third thing that inflation does, apart from flatness and size, is it also explains the origin of the fluctuations that give rise to structure. So these fluctuations are thought to be quantum fluctuations. But inflation, with this exponential expansion, blows them up into macroscopic scales, and from then the galaxies are seeded. So, and that looks something like this. Okay, so imagine this is the scale you're studying the universe from. Going from small to larger scales. Okay, and these are the initial conditions that inflation provides. So this will be zero or negligible without inflation. Inflation gives you macroscopic fluctuations. And in this simple theory, the initial theories, they said there were just one number explains everything. Some random fluctuations that are the seeds of everything. Now what the universe does is expands. It acts like a filter. It takes this initial uniform fluctuation distribution and filters it because the early universe was full of radiation. And that radiation basically inhibits fluctuations from growing. You have to wait until the universe becomes atomic. The radiation decouples and then things can develop rapidly. And so all the fluctuations in the early universe up to a certain scale defined when the universe first became matter-dominated. They're all roughly the same, the maximum size. And the larger ones grow later because they just enter the causal region a bit later. Okay? So this is very interesting because it translates into density fluctuations. And here they are, this plotted slightly more precisely, that's this green line. So this is the prediction of inflation theory, that on the small scales, and this will be subgalactic scales, you get fluctuations which develop first, and then the bigger scales develop later. So we call this a bottom-up theory of structure formation. And the remarkable thing is that you can now use data, and the data includes the microwave background on the larger scales, and galaxy clusters, and galaxies on smaller scales, to trace out the data that fits this simple curve, and you can see it fits reasonably well. Okay? So one actually can verify at a simple level, at least today, one of the key predictions of inflation theory, that you should have some fluctuation distribution, nearly scale invariant, that turns into the structure we see. Okay, so how do we actually prove that these fluctuations are really there? So now let me get into the heart of the story, actually, how these fluctuations were discovered and what they mean in the fossil radiation. So this is a way to see how this works. So I talked about waves in this plasma early on in matter radiation. We imagine various waves, okay? This represents the growth of fluctuations, and this is dark matter. So dark matter, which is this new ingredient, we think is some sort of non-interacting particle. So it just keeps on getting, the fluctuations grow as gravity operates. But here we have in the plasma, that's the ordinary matter, okay? Baryons in radiation, they act like waves. Okay, this represents waves. And then what happens is, after 300,000 years, when the Big Bang suddenly neutralizes, the radiation decouples from the matter, the radiation streams freely to us, we measure this radiation with our telescopes, we measure the fluctuations with our telescopes too now, then these imprints are left in the radiation, and these baryons then, along with the dark matter, can form galaxies. And what is really interesting is the dark matter, because it has doesn't connect with the radiation, keeps on, the fluctuations get stronger and stronger, it actually gives a boost to the baryon. So dark matter plays a very important role in understanding why we're here and why the fluctuations have whatever level they have, which you need to explain structure. Okay, so I entered this field when I was a graduate student, and this was one of the first papers I wrote, called Fluctuations of the Primordial Fireball. And I realized in those student days, that's my thesis basically, that to make the fluctuations, they should be observable if one wanted to explain the structures. There was a simple connection with fluctuations. Now it's interesting, at this time, my thesis was supported, I was at Harvard, by a grant from the US Air Force. Now I don't know that would ever happen today, but in those days, it was an interesting sort of way of supporting science. The US Air Force, the US Navy too, were very generous in this sort of side. Anyway, so things have changed, of course. And then the next thing that happened was that dark matter was realized to play an important role. That happened a decade or two later. And then a couple of these papers, one of which I was involved in, made the predictions for what we currently believe are what matches the current data. Okay, so why did it take so long, 1967, 1984, for the fluctuations to be developed? It took another decade for anything to be found. So the reason is here. The theory got better and better. Okay, so these dots are the theory. Okay, it got more and more precise. Okay, so here was dark matter was introduced. Okay, and so forth. And the observers had to work harder and harder. So in the early days, Penzias and Wilson, they said it was isotropic to roughly 10% or something, and people realized there was something to check for there, and they worked. But it was a story of upper limits. And you can see this is a graph taken from the post-Kobe days, 1992 or thereabouts, okay, where you can see this enormous scatter in the underlying data. And it's interesting, all the physics that's tied in with these fluctuations. This is the temperature fluctuations as predicted from the simple theory, and this is basically what gives you the first structures. The first structure that develops. This is roughly the scale of galaxies, and finally you have the smaller fluctuations damping away, which is one of the things that I worked on in the early days. Okay, so this was how things were, but things have got immensely better. So this is now progress in probably, I would say, less than 2 decades. So this is a progress. And it is amazing to look at the difference. So here are these waves. You can see they leave their imprint on the radiation field. You expect these, and they gradually damp away on small scales. And so with the latest telescopes, including one at the South Pole, you can measure these ripples all the way. And each one of these represents a different wave. And this is the main wave, the primary wave that first enters the horizon, the scale that light can travel since the Big Bang when the universe first went transparent. Now, one of the most amazing things that's come out of this theory and data is that we've proved to very high precision that space is Euclidean. Space is flat, we say, in a simple way, okay, like the geometry of a sheet of paper as opposed to geometry of a sphere. How do we know that? Because when you look at the microwave background, this represents the universe long ago, and you're looking at some scale of the microwave background, it might be this scale, for example, determined by local physics. If light travels in a straight line in a flat universe, but in a universe that's curved, like the surface of a saddle, we call this an open universe, the light is bent like this. And that means that this scale should be shifted, okay, to larger scale. It's not. And the fact that it's on a certain scale measures directly the geometry of the universe, with one or two slight complications, which we think we can control. Okay, so you can read on the sky the Euclidean nature of the universe, okay? So that's one outcome. The second outcome is that what these fluctuations do now is they provide you with the seeds of galaxy formation. Now, how do you implement this notion of seeds? Well, these days you do it on a computer, okay? So you take these fluctuations, you translate them via the Boltzmann equation, density fluctuations. You get these density fluctuations to come out. So here are the density fluctuations, and you notice it's just like, I should say this line that goes through these points is exactly the simple line that corresponds from the inflation theory, okay? That's one of the simplest inflation theories. And these same fluctuations can give you the density fluctuations, and you can also measure the density fluctuation directly from large-scale galaxy surveys. So there are two types of fluctuations plotted. You can't tell them apart at this resolution, and you can see that, again, on small scales, things form first, they're larger, and then things develop on larger scales. So this is the basis of that bottom-up theory of structure formation. And what one does is if you blow this up a little bit, you can see that not only in the radiation, but in the matter as well, you can see these wiggles, okay? So the wiggles in the matter are these should be green points over here. exactly in phase with the radiation wiggles. So again, an amazing thing. We're seeing the imprint of these primordial sound waves in the universe around us, as well as in the fossil radiation. And so what this has led to then is you can now do an n-body simulation, a computer simulation of the universe. Okay? So this is a huge simulation with some billion particles or so, representing point masses, galaxies, whatever. You let it run with the initial conditions of density fluctuations in the very early universe, and you watch self-gravity do its thing. So what happens is that in a region with slightly more particles, it's slightly denser, they pull in more particles by gravity. It's like the rich getting richer, and in the emptier regions, they lose more particles, things flow out of the voids, the poor get poorer, etc. Just very complex work through. Anyway, on here you see a comparison of the real universe with the simulated universe. And you have to stare at this a while to figure out which is which, actually, and I always forget. So the red is the simulations, filtered the same way as 3 different observational surveys. So one of these is the Sloan Digital Sky Survey. This is the Anglo-Australian 2DF survey. This is the original, the pioneering CFA survey. This thing over here is the Coma cluster of galaxies with the distortions I mentioned earlier due to the effect of random velocities. Okay? So you can see it's very hard to tell them apart. So what this tells us is that we really have a very good model of the large-scale universe. And we conclude from this that all of this is in the presence of the dark matter, which controls the growth of structure. It's a dominant effect. And so not only have we got the fluctuations right, but also the dark matter is something very weak interacting. Otherwise, things just wouldn't look like this. And effectively cold in response to gravity allows gravitational things to collapse. Of course, there is a big question mark, which I'm not going to address very much here, but we don't know what the dark matter is. That's a problem for the future. We have yet to find it. But nevertheless, we're sure it's there, and we're sure of its basic properties. Okay, so let me now turn to another component of the universe, which is even more dominant than dark matter. And so let's go back to Einstein. And here we have Einstein and his famous equation. And here is Einstein's constant, which he introduced to give you repulsion. This is gravity, this is anti-gravity. He wanted to stop the universe from collapsing. Well, nowadays, with the acceleration of the universe, we think we've found anti-gravity. But how do we interpret Einstein's lambda? Okay, so there's a very simple way to do that. It's simple algebra. So you take this and you stick it over here. Okay, so this is energy momentum. And here is Einstein's lambda term. The sun we call, and this now we can call dark energy. It's not energy we see, we call this dark energy. So Einstein's repulsion is now dark energy, and we're desperately looking to try to identify this. Okay, so what have we seen so far? So what we've seen so far is the following. When you look at distant supernovae, and this is getting back to the Nobel Prize, or what a week ago, that the supernovae far away are too faint by about 25%. And so what you're measuring now is the difference between essentially dark matter and dark energy, because the effect of repulsion is accelerating them away, making them fainter than they otherwise would be. They're further than they otherwise would be. Okay. So that is fine. So from supernovae, you measure the difference of dark energy, dark matter. From the microwave background, you measure the curvature of space. Now, curvature involves all the energy content of space, dark energy and dark matter. So there's a plus sign over there, minus sign and plus sign. And finally, with the lensing I told you about, the baryon wiggles, that gives me just the dark matter. Okay. Again, I'm simplifying slightly, but we now have 3 measurements of 2 different things. So the problem is over-constrained, and this, I think, is why the Nobel Prize is given, that we basically can now plot dark energy, dark matter. We have 3 lines, and they converge in one very precise point. The unit is 2/3 dark energy and 1/3 dark matter. Okay, so that's where we are observationally. And to summarize that mix, dark energy 75%, dark matter, cold to make galaxies 20%, and a sprinkling of atoms to make us. Now, let me now turn to the implications of this theory, which are very, very serious, okay? Okay, so you can calculate what you expect the dark energy content of the universe to be from basic physics, okay? From particle physics. And this is the number you come up with, okay? This is what we call the energy of the vacuum. This is what you expect from the gravitification theory, etc. The theory, string theory, whatever theory you have at the beginning, this is what it gives you. Unfortunately, what we measure in the data with the supernovae is this number over here. Never mind what the units are, but you can see the difference, I think. There are 120 factors of 10. So this is the biggest discrepancy that we've ever come across in physics, I think. Okay, it's been called the greatest problem in physics. So how on earth do we try to address this? Okay, so this has led to many, many speculations, and let me summarize what is probably the most popular one among my colleagues. It's called the multiverse theory. And so the idea is that inflation occurred not just once, but occurred many times. And so here we have, this is our universe over here, okay, this is all we can see in our inflation universe, but it's part of some superspace. We know back to Kaluza Klein theory, and all these are embedded in some high-dimensional superspace, okay. But there were other episodes of inflation leading to other domains and other universes. So we have a vast number of universes. Okay, so if we have enough of these universes, and we need at least 10 to 120 of them, then you can make the point that our particular domain is just one of some vast number. The typical value may be out there. We're not living in it because that universe that had so much dark energy has collapsed. We're in a universe that's lasted long enough for us to have developed as observers, for example. Okay, so this then has led to this point of view, which is sometimes called the anthropic perspective, principle, in which here we have our one happy universe, and what Susskind and others have argued is that we happen to live in one tiny pocket of the universe where the value of the cosmic constants is consistent with our kind of life, meaning that if it were much too large, it would have collapsed long ago, there would not have been time for life to observe. Now this is clearly a very imprecise statement, but nevertheless, it so far is the only way that we've actually been able to address, in any statistical sense, this question of the paradox between theory and observation. Now, this is by no means universally accepted, and for example, the counter view is that this theory, the multiverse theory, cannot make any predictions. This has been said of string theory too, for that matter. It's even more true of multiverse theory, because we can't see the other units in the multiverse. They're outside our horizon, outside our past light whatever. We're never going to see them. So it can explain, he says, it can't make any predictions, George Ellis, it can explain anything. So that means it's not really physics. Okay, so we are left with this viewpoint about cosmologists, often in error, never in doubt, Xander said. And if we don't want the anthropic viewpoint, then we may hope for a fundamental physics theory of dark energy. That is yet to come. We see no sign on the horizon, but I think that just waits for cleverer people that the next generation of brilliant physicists, I suppose, or beyond. Or we have some astrophysical explanation, which so far has not been found, but it's not impossible that there could be such a thing, I think, at this point. Okay, so in the last minutes, let me now revisit the question of galaxy formation, which is another unresolved mystery, I would say. I mean, it's really important to understand. I gave you in broad outline how galaxies form from tiny fluctuations. What about the details? Why is the Milky Way the way it is? Okay, full of stars, etc., full of dark matter. How does it come out to be the way it is? And there are some, beautiful galaxies out there. Can we understand beautiful things like this, which are forming stars? Probably lots of dark matter. How do things like this come about? Okay, so let me then take you through the idea of gravitation and stability. So this is again a trip through history, and it begins with Isaac Newton, actually, who was the founder of the concept of gravitation and stability, how fluctuations can develop into, in his case, planets and stars. And so in unpublished work, okay, this is a story of unpublished, in letters, okay, to a clergyman who's praying some lectures on the origin of the world, he wrote the following, that he imagined that if matter was evenly disposed throughout an infinite space, it would fragment basically into many masses, okay, to make an infinite number of great masses, scattered from one another. And he thought, so might the sun and fixed stars be formed. Okay, but then Newton ran into a problem. He realized that there were planets as well. So how could he make stars, shining objects, and opaque things like planets? And he gave up at this point, and he says he didn't think this could be explained by natural causes, and he said, let me appeal to some higher authority. Okay? He was a religious man, okay? And things stayed there for a century or two, a couple of centuries, and then the next person who had a very different point of view was Jeans. And so James Jeans, around the turn of the 20th century, developed the notion of gravitational stability in a quantitative way. And so his idea was that if I have some immense region full of matter with fluctuations in, then it's a battle between pressure of the gas and gravity. And there's a critical distance, which is the distance a sound wave can cross in the time for matter to be assembled by gravity. And if things are larger gravity winds, things are smaller pressure winds. And we call this critical scale the gene scale. And of course, Jeans was very much an agnostic, okay, or something. The universe now appears to be a pure mathematician. Okay. Anyway, so here we are again, repeating this figure. Gravitational stability is the link between the fluctuations and the structure that we see. Okay, so that seems fine. Okay, but now let me take you very briefly through one detail. Okay, so this is the result now of an n-body simulation, which shows you the principle of how you make structure in a bottom-up way. Go from the universe when it was Redshift 3 to today, 1/4 billion size today, and you see there are large-scale filaments. We understand this from our simulations, from gravitational stability. The cold matter, the dark matter, and the baryons really do aggregate in a very interesting way. And in these slightly denser regions, the first galaxies form. Okay? Then as time goes on, the galaxies form around them. And as more time goes on, the galaxies that form here, their stars age, and the galaxies actually redden, because older stars like the Sun are redder than the young blue stars. And then finally today, you have what's a galaxy cluster over here, surrounded by younger galaxies outside it with ridges, etc. So this is our standard prediction of the universe, and it fits in beautifully with our theory of the fluctuations, etc. Okay, in a general way. But if you look in more detail, there's a huge problem. Okay, there's one thing I haven't told you. Although there are galaxies in this picture, they're painted on in the simulation. They're not intrinsic in the hydrodynamics. And so if you try to compare now a state-of-the-art simulation with a galaxy, this one is one observed by the Herschel Space Telescope recently, in the last year or so, it looks nothing like it, right? This is a galaxy, but only dark matter in the simulation. This is an example of a discovery, one of the very few discoveries that was made by a computer simulation. This was not realized before the days of massive simulations because, 30 years ago we thought that a dark matter halo was just some amorphous dark blob. But from the simulations we realized it's full of tiny blobs, okay? These are lumps of, because the dark matter is really cold, it clumps, okay? And so all these many clumps, we don't see them. Where are they? They don't have baryons in. And this concentration in the center, where is it? Okay, so this looks nothing like this. Okay, so that's a problem. And the reason is simple. There are no baryons in the simulation. Why not? It's extremely hard to put baryons in the simulation. It's pushing our current numerical capability beyond where it actually is now. People are beginning to do this. Okay, as I speak, they're beginning, but so far it's not been done properly. Okay, so the solution is the following. We believe that what you need is what we call feedback. Okay, feedback is common in many fields of physics, but in this big example, you need the effect of the first stars that are made to blow the baryons out, and that leaves all this dark stuff behind, mostly invisible. Okay, we may see traces now and then, which are good, but mostly, what is the feedback when it comes from exploding stars, for example? Okay, so here is my example in a simple way of how this might work, again, from first principles. This is data, and this shows you the distribution of galaxies by luminosity. We call this the luminosity function of galaxies. Okay, the numbers of galaxies as you go to very bright ones, very faint ones. It's a curve which is flat and then falls up, steepens. So it's this blue line on this curve. The theory line is the red line. Okay. Okay. So the theory line comes from a pure dark matter simulation. Okay, the best we have. And you notice it's a complete disaster. Okay, if you want to say that light tracks mass. Okay. It fails everywhere except possibly for one point if you readjust it. Okay, so that's the bad news. The good news is that at this one point it actually works. Now, why does it work? Well, if I take, there are only two time scales in this problem. One is the time it takes a gas cloud to lose energy and cool down, which it has to do to make stars. And the competing time is gravity, the time for the cloud to collapse. So all I'm going to do is compare the two time scales and rewrite them. Okay, it's not magic. And when you rewrite them, you can write them in terms of fundamental constants. One of these is called the gravitational structure constant. Let me not go into that in detail. And it turns out that when you rewrite them, this automatically, if I require the cooling time to be the dynamical time, that's the maximum scale for a galaxy, lo and behold, it gives me roughly the right ratio of mass to light to fit this point. So that's a great success. I think in a simple way for the field of galaxy, we've got the scale right. We've got the average scale of the galaxy correct, okay, in terms of baryon physics. But we haven't got right in all the rest. And how do you do that? Well, we do that with feedback, and it's complicated. And this is why the simulations have not converged today. On this scale, you have exploding stars blowing the baryons out. On this scale, exploding stars don't work because these are massive galaxies. They're deep gravity fields. You have to use massive black holes, accreting gas, blowing out enormous winds and radiation and blowing the gas away. So feedback, well, active gravity nuclei by supernovae. And neither one of these is that well understood numerically. Adding them both together is a nightmare. And I would say that we are just beginning to scratch the surface. It's promising, I think, very promising for the future. You can imagine also this fits in beautifully with the new generation of very big telescopes, because you see these phenomena going on in the early universe. The bigger your mirror, the better to see these things very far away. Okay, so here are the problems. Here's one of these state-of-the-art simulations, again without the barrier, showing you how structure assembles. Okay, too many massive small galaxies, too many baryons in the galaxies, got to blow them out somewhere. That's another indicator that feedback must be occurring. But the ultimate problem is that we have finally no understanding in a fundamental way of star formation. We cannot predict from fundamental physics the masses of stars. You know, a lot of astrophysics goes into it, you know. And one of the fundamental things is the mass of stars. We call that the birth function of stars. That tells you which stars explode, which stars give you the chemistry, etc., which stars give you the light. We have no theory that tells us that's the same ever in the universe, or might vary from place to place. And that's one of the weaknesses in trying to make a theory of galaxies. Okay, so let me close then with discussing the future prospects, where we're going. For dark matter, it's very exciting, I think, that we believe it's some sort of weak and elementary particle. We've yet to identify it, and it's led to a whole new field of physics, called particle astrophysics. And we're pursuing this field with very strange telescopes, unconventional. This one is deep in a mine, deep underground. This is like no other telescope you've seen. A collection of metal plates, but designed to look for gamma ray, Cherenkov flashes from gamma rays in the atmosphere. This one's in Namibia. Deep under ice in the South Pole, or deep under the Mediterranean, and in space using a gamma ray telescope. So all of these are ways to look for traces of dark matter. Why? Because the dark matter every now and then interacts with itself. It gives you flashes of light, flashes of gamma rays, according to the standard theory of dark matter. Not the only theory, but if we're lucky, then we may see indications of dark matter. There are hints and intriguing hints at the moment, but nothing has been seen. As far as dark energy goes, that's a whole other story. This needs incredibly larger and larger telescopes, I think is the bottom line. We have to go to a 30-meter telescope, maybe. This is the planned Hawaiian telescope, US. We have to go to a 40-meter telescope. This is the planned European equivalent. And we have to develop new types of wide field telescopes, better surveys. This is another space telescope recently approved in Europe, also to do space-driven surveys, and finally the Planck satellite, which is taking data now and hoping to add to cosmology and to improve our knowledge of what dark matter might or not be. As far as galaxy formation goes, I think that what we need simply is better resolution, better physics, and the better resolution will give us the way to do better physics, both in the simulations and the observations are very, very far away. To get things as beautiful as this is the Andromeda galaxy. How on earth do we get this detailed structure, stars forming, etc., and gas and dust? It's a complex thing, and we need better simulations to take us from the initial conditions to the endpoint. Okay, and then finally, the future of the universe. Okay, I'm going to end with this. Thanks to the discovery of the acceleration, this was the future we might have imagined before the acceleration. As we'll be seeing, as it expanded, more and more things will be visible as time went on. But now it's a very, very glum prospect. In 140 billion years, there will be just one galaxy inside our horizon. Everything else is accelerating away from us. So that's all we have, and well, but it's a long time to go before we're in this position. Then we'll stop doing astronomy, that's for sure. Okay, so thank you.
So thank you very much. I'm sure there are some questions. No questions from the audience? There.
Okay, I'm going to try one I tried last week. It's a two-part question. The first part is the universe homogeneous? Is it isotropic? And is it infinite, as you hinted to earlier in your speech? And if those three answers are yes, why would Einstein be worried about the collapse of the overall universe due only to gravity?
Okay, so to a first approximation, it is homogeneous and isotropic. We have no idea whether it's infinite observationally, we could never tell. Einstein would have assumed it was finite because he had concepts of island universes that were current at the time. And so he was very worried about the collapse of the universe.
So what's the most interesting result you expect from the Planck satellite?
Okay, so I think there's a good chance they're going to measure the spectrum, the power spectrum, the slope of the power spectrum. There are already hints that it's not completely scale independent, which is what the theories before inflation predicted. And post-inflation, we know it depends on scale, and I think there's a very good chance that Planck's satellite may verify that with high precision. If it does, that will be a very interesting development supporting inflation theory. The other hope is that Planck will measure gravity wave backgrounds, which are another prediction, but I think that's very unlikely. There are other experiments with that.
Thank you for a very nice lecture. I have a question about a picture that you showed earlier, and I do not know a geometric name for it, but there were like big bubbles next to each other, which explain what the universe would look like. Would you mind backing back to that picture so that everybody knows what I'm talking about?
Sure. Okay. This one, right?
Yes, that one. I, of course, find it very interesting, and I understand it's very theoretical, but I have a question about what about in between, the white space? What is it there?
Okay, right. This is what my colleagues in string theory might call the bulk. So I'm not really qualified to tell you what's there, but that's not really my domain. But you have to imagine that this is in some higher dimensional universe, a higher dimensional space, and that these are particles in this higher dimensional space. And so just as in our three-dimensional space, there are separations and gaps and so forth. So in this higher dimensional space, there are gaps between regions populated by universes, and exactly presumably there's nothing in there. Certainly nothing.
Some cosmologists think that time started with the Big Bang, and some say that there was something before. Do you have an opinion on this?
Okay, so I think it's very likely that time started before. There's nothing special about time having to start with the Big Bang. But there's no theory at this point of how you get through from the previous cycle to the current cycle. So it's a question of how far can you believe your theory, and I think believability more or less starts with the Big Bang at this point, that instant at which things are expanding. But as before it's conjecture, it seems likely there was some previous phase, to me at least. No one has yet a theory that, I think a robust theory at least, that enables us to specify that.
I have a new question. Has the relationship between the redshift of light and distance been confirmed in any other way? Meaning, has anyone ever measured the density of galaxies at far redshifts and compared them to the density of galaxies in the local region to confirm the fact that space is in fact expanding?
So there are measurements of density decreasing. It's confused, though, by the following problem, that when galaxies, you're looking further away back in time, because the further away they're younger and brighter. So you have to separate evolution from this effect. So it's not completely clean. And I think the ultimate test will come with a new spectrograph that's being prepared, designed for the European Small Telescope, which will have the ability to actually look at a pair of quasars and actually measure their real-time separation by repeating the observation over a year or two. So someday we may have direct measurement expansion. But right now it's indirect, it fits into the theories, but I would say, I'm not sure there's any... there's one other observation which I think is essentially proof, and that is one of the effects of expansion. The further away something is, because of the redshift, it gets dimmer. A surface brightness gets dimmer. That effect's been seen. And so that basically is probably, at the moment, the most direct measurement of expansion of the universe, the dimming of distant galaxies. Because it is confused a bit by evolution aspects. So.
So I have a question related to this graph as well, which you may believe in or not. Do you think there's a risk that we'll never know what dark energy is or what's driving the acceleration of the universe? Yeah, this scenario.
There's certainly that risk, but given the history of physics, whenever there's a challenge, eventually it may take a long time to find a solution eventually. So I'm confident that we'll get there. When I can't possibly say.
Okay, so let's hope Raman was happy with future career choices. Do we have any more questions? Yeah.
One model of the universe is that it's a 3D sphere. That is it's a three-dimensional surface of a four-dimensional board. Do you have any opinion about that?
No, I mean, there'll be a compact universe. I mean, in principle, we can have a universe that's compact, and there are many other topologies that are possible too. Einstein's theory does not predict the topology of the universe, so that's a whole other stream of possible universes that I've been touching on.
Okay, so if there are no more urgent questions, then I propose we thank you again. We have one little detail as well, of course, the medal. So those of you that want to see how this medal looks like, you have to come forward later, so take a look. So on behalf of the Oskar Klein Memorial Lecture Committee, I hereby present this medal. And thank you very much.